There are lots of different things in the physical world around us that we model sinusoidally. It could be the voltage or current in an electrical circuit. It could be vibrations of some sort of a mechanical system. We could be referring to the propagation of light energy or electromagnetic energy. So in this video here, I'd just like to review with you the various parameters or the various markings of a sinusoidally varying signal. By sinusoidally varying, I mean anything that could either be modeled as a sine or a cosine. So for example, let's just talk in terms of voltage. As I'm an electrical engineer, let's talk in terms of voltage. It's a time-varying voltage that we would model as having some amplitude V sub m times this cosine of omega t plus some phase angle phi. Alrighty, what does V sub m refer to? Well, first of all, what is cosine? Well, you know that the cosine function varies from -1 to +1. So if you multiply that plus or minus 1 by some constant V sub m, then we have a waveform that's varying between negative V sub m and positive V sub m. In this picture right here, we've got down here at -5 and on up here to a +5. We refer to this amplitude, or this distance here from where it crosses the horizontal axis on up, we refer to that as the amplitude. Amplitude of the wave, and for our model, that amplitude is V sub m. Now this waveform varies periodically, and that means that it repeats itself every so often. The period is the length of time that it takes to go through one of these cycles, or until it repeats itself. So we could say then that we've got a distance from its peak on the top to the peak on the top would represent one period, and we use the letter T, capital T, to represent period. So T is the period of the signal, and it has units of seconds, or time to be more accurate. So from peak to peak is T, from negative going zero crossing to negative going zero crossing, that's another interval of T seconds. Or we could talk about from positive going zero crossing to positive going zero crossing. Again, that would represent one period. Now, if instead of talking in terms of time, we talk about how rapidly this signal is changing, we refer to its frequency, and we use the letter lowercase f for frequency. It has the units of cycles per second. And if you stop and think about it, if the period is the length of time that it takes to go through one cycle, it would be so many seconds per cycle, then frequency, the cycles per second, is just equal to 1 over t. And that gives us a frequency in cycles per second. Common in electrical engineering, we might talk about 1,000 cycles per second. Another term for cycles per second is hertz. 100 cycles per second, or 100 hertz. 1,000 cycles per second, or a kilohertz. Or 1,000,000 cycles per second, 1 million or 1 megahertz. If you think about the FM radio dial, say you're listening to some radio station that's broadcasting its FM 96.3, that's referring to a carrier signal that's oscillating at 96.3 megacycles per second, or 96.3 megahertz. Now, the argument of a cosine or a sine wave is frequently measured in terms of radians per second. So we introduce another frequency, or type of frequency, that we're going to call the radial frequency. And the radial frequency is in radians per second, and that is equal to, because there are 2 pi radians per cycle, we can calculate omega by 2 pi times f. Dimensionally, let's just look at that. If f is in cycles per second. And radial frequency is in radians per second. We need to convert from cycles to radians. Well, we simply multiply by 2 pi radians per cycle. Cycles cancel, and we're left with radians per second. So we have amplitude, we have the period t, we have the frequency f, which is the frequency in cycles per second, and we have the frequency omega, which is in radians per second. There's one final parameter we want to introduce, and that is the concept of phase. We mentioned that we model this in terms of this v sub m cosine of omega t plus some phi. Phi we refer to as the phase term. If you go back to your college algebra, you'll remember that if you have some function f of t, then f of t plus some constant was simply the function f of t shifted by c units. Now, if c is a positive number, then f of t plus c represented a shift of the original function f of t to the left. And if c was negative, it represented a shift of f of t to the right. So here we have our original function, v sub m cosine omega t, in the blue. And we've got this red function here, which, if you'll notice, it happens, it's basically the blue function shifted to the left, in this case by 90 degrees. So the red function could be written in terms of the blue function shifted to the left, or we'd say that the red function is v sub m, it has the same amplitude, cosine of omega t, it has the same radial frequency, but it's been shifted ahead by 90 degrees. Now, we electrical engineers get a little bit schizophrenic here because we do mix our units. And sorry, that's just the way it is. You're going to have to get used to it, I guess. Omega is in terms of radians per second, and phase frequently is given in terms of degrees. So how do you convert from degrees to radians? Well, once again, let's just take the dimensional analysis approach. And so if we have degrees and we want to convert to radians, we multiply by something that's going to have degrees in the denominator and radians in the numerator. And so then we have to say, all right, well, how many radians are there per degree? Or we know that there are 2 pi radians per 360 degrees. So to convert from degrees to radians, we multiply by 2 pi over 360 or by pi over 180. In other words, degrees times pi over 180 equals radians.